Hi, algebra students. Today we're going to talk about just generalizing how we can get the best line of best fit. So the last couple of lessons we're kind of trying to eyeball it. We know it's not always necessarily very accurate, especially if we're having to estimate when we plot the points. So we want to come up with a way that's much more accurate. So let's take a look at this data here. It says the following table shows data for one season of the El Toro professional basketball team. El Toro team member Antonio Cusack was inadvertently left off the list. Antonio played for 2,103 minutes. We would like to predict how many points he scored for the season. So you can see all the different players' names and then how many points they scored in the season. So over here at the right, I already have those points plotted. You'll notice that they're kind of clustered here, and then you kind of have these outliers that are much higher than the rest of the points. So notice my scale, like because the range was the intervals were like so broad, right? I have this is really low and then these are really high. And so the scale is kind of like it's going by 500s because of that. So I already sketched in my estimate for a line of best fit. And it's really hard to plot on a scale like this, right? When it's the intervals are so like you're going by 500s to estimate where like 7.5 falls is really difficult. But I've already drawn my line on here. And the first question is asking, okay, well, which point appears to be an outlier and whose data does that point represent? And then what is his residual? So I would say like this one's all the way up here. This is the highest one. So this must be Scotty, right? So this is Scotty Sorden is our outlier. And his point is the 3,090 and the 2,491. So what we want to do first is, okay, we're going to do it again. We're going to find our line of best fit. And then we're going to figure out what this is his actual. So when he played 3,090 minutes, this is right here, the actual number of points he scored. So we need to find the predicted. So what I did was I already went through and I picked a couple points that fell nicely on the line. So let me just jot down. I did this already ahead of time because, okay, we know the drill on this, right? I'm going to just write it over here. So I have 2 points, 3,000, 1,000, and then 545, 182. That's actually one of our data points that the line went through pretty nicely. And this was a lattice point. So what I'm going to do is I'm going to go ahead, I'm going to find my slope, my change in y over my change in x. You can make a table, or I can say I see from 182 to 1,000, that went up by 818. From 545 to 3,000, that went up by 2,455. And if you divide those, I get 0.33 for my slope. For my y-intercept, I'm going to go ahead and use this point here. I just like the numbers. They were easy to work with. I'm going to plug in my slope. This is, I don't want it to be 1,000, I want it to be 3,000. Okay, so not only is this kind of tedious, but not super accurate because of all of the estimating that had to go into finding the points and graphing the points. Okay, so this is 990 right here. So then B is 10. So my equation is y equals 0.33x plus 10. So I'm going to come over here, back to Scotty, and I want to figure out my predicted number of points when he is playing for 3,090 minutes. So I'm going to use that equation that I just came up with. So my x is 3,090, and his predicted number of points that he will score is 1,020. Okay, so residual, remember, is when you do the actual amount he scored minus predicted. So he actually scored 2,491, but it was predicted only that he would score 1,020, right? Because his point is way above the prediction line. So we should kind of expect that. So our residual is 1,471. So now it's asking, would a player be proud of a positive or a negative residual? So if you were only predicted to score 1,471, but then you scored way more, then or I'm sorry, you were predicted to score, only 1,020, but you predicted way more, that's what would give you a positive residual. And that's pretty good, right? The prediction was lower than the actual. So you actually did better than predicted. So I would say in this case, a positive would be better. So in this case, a positive residual means the player is scoring higher than predicted. That's a good thing, right? For the team, that's a good thing. So depending on the situation, sometimes higher residual is better, sometimes lower. Well, now remember they had told us about Antonio and how we knew that he's played for 2,103 minutes, but now we want to know how many points he scored. So now that we have this model, this y equals 0.33x plus 10, now I can substitute in that 2,103 for x, and then he would have scored about 704 points. Okay, so the whole point of getting that predicted model is to be, or that line of best fit is to be able to make predictions. So we have this model to predict things. But I think you would all agree that, this is not necessarily the best line, right? Because we're doing so much estimating. So what we want to do is figure out a way to get a consistent best fit line for data. And this can be found by determining the line that makes the residuals, and therefore the square of the residuals, as small as possible. So if we look at this is all the data. Okay, this is the data from right here. And if I look at my line, y equals 0.33x plus 10, what I want to do, so like if I were to graph the residuals, if I were to figure out where the residuals are in here, like that's the distance between the point and the line. So do you see how here the points are really close to the line? This is on the line. This is really close, really close, really close. So right now, if I were to figure out what the residuals were and added them up, they would be pretty close to zero. But then here, look at this residual. That's a big leap, right? From here to here, from the actual to the predicted is really high. From the actual to the predicted is really high. So what we're trying to do is come up with a line that will minimize the residuals. And it mentioned on the notes there the square of the residuals. Because what we want to do is like not take into consideration like this is negative and this is positive. So we would think of it as squaring. So it's really kind of a very complicated process. Instead of going through that really complicated process, what we're going to do instead is we're going to use the calculator, because Desmos will actually do this for us. So the process that the calculator is going to do for us is called the least squares regression line, and we're going to abbreviate it LSRL, and our calculator can do it quickly. So the process for doing it is like for each of these data values, we would have to find the predicted value. Then we would have to subtract and we'd have to get the residuals. Then we would have to square the residuals. Then we would have to, it's like this huge long process, and the calculator will do it for us. So we're going to use the calculator to help us. So if you look here, right, these are all the steps. So the first thing is that you're going to open your Desmos app or go to www.desmos.com. You're going to press the plus sign and choose table and enter the data. I have it linked here, but I'm going to show you how to do it. And then we're going to choose to add an expression. And this is how we're going to type it in. So in a line in general, the equation is y equals mx plus b. Okay. So when you put data into your calculator, it's automatically going to label the first set of data like x1 and y1. Like your first set of x's, your second set of first set of y's. And if you look at this, Desmos doesn't use M's and B's. It's going to use A's and B's. You can see that here. So the MX is like this part here, A times whatever is in your X1. And then here's your B. Instead of just saying Y equals, it's Y1 equals. And then the other thing I want to draw your attention to is this little symbol here is a tilde. That means approximately equal to. Okay. So this on your keyboard is next to the number 1, or if you're using the Desmos keyboard, it's in the ABC menu. I'll show that to you. All right, and then it says the A and B values that show up under parameters, we're going to substitute into this equation for A and B, and then that will give us our equation in decimals. All right, so let me show you what I'm talking about here. So I already, like I said, I already have the data entered and I had entered this one, but let's go through this together. Okay, so the first thing it said was to hit the plus sign right here, plus and table. Okay, and you see this is what I was talking about. So it says X1 and Y1 because it's your first set of data. If we were to create a different table, it would make them like X2 and Y2. All right, so then we're going to, just from our notes, we're going to type in the data. And I'm going to do all the X's first. And all the Y's second. I'm doing this kind of quickly, and then I'll go back through and make sure I didn't screw anything up. Okay, and then enter in all of your Y's. You can see those data are popping up. You do want to make sure, especially you're typing in all these numbers, it's really easy to screw something up. Let's see, like this one is supposed to be 1641, not 1651. 64. So do make sure that you're going through and making sure that you typed everything in correctly. All right, so that looks good. So there's all my data. And right now, I already had my window set so that I would be able to see it all. If you can't see all your data, if you click on this little wrench here, you can set your x-axis to go up how far you want. So you could set it to go from like -10 to then look at what your highest x value is and make sure you go a little past that, right? And then same thing here, you could say I want my y's to go from -10 to like, I don't know, 2,500 or something like that. So you can see all of your data. So the wrench is where you can set your viewing window. All right, so then the next thing, I want to go to this next line here, and now I want to add I want to write an expression. So what I'm going to type, right, what we had said on the previous page is we type y1 and then the tilde key, which is next to the number 1, so approximately equal to. If you're using, where is it on here? If you're using like the Desmos, the little keyboard button, when it pops up, it's in the ABC menu, and I have a feeling it's behind my little Screencastify thing right here. All right, then we have B plus AX and then 1. Okay, and so what that does is it creates the line of best fit. Okay, so that's the line that would reduce the residuals as much as possible. Now, to get a better line, we might want to throw out these couple of outliers, but this is the line that would reduce the residuals the most. So to write our equation, so you look when you put that in, do you see you get all this stuff here? Okay, so it gives you this R squared and R value. We'll talk about this later. If we want to plot the residuals, we could. Those little black points are the residuals. Okay, I want to get rid of you. Oh, what do I want to do? Okay, so I can go down here, I think. There's a way to get rid of them. Oh, the residuals, I can turn them off by clicking here, so I don't want to see them. They're kind of muddling my view, but it will calculate the residuals for you if you want to see what the differences were, and it will plot them. And then it gives you this A and B value right here. And that's what we're interested in, because our equation, we're going to plug in this negative 200 and what is it? Negative 208.736. That's our B value, and our A value is 0.594 or 5. I would say 5. The 6 bumps up to a 5. All right, so coming back here, it says, all right, now get an equation for the problem that we were just doing. We would say, all right, it says use the A and B values under the parameter to write your equation in y equals B plus AX form. That's the same thing as slope-intercept form. It's just that it's using like this M. This is like my M right here. So if you want to write it in MX plus B form, or really you can think of it as AX plus B form, that's fine also. So from where it said parameters, it said our A value was 0.595x and our B value was negative 208.736. That would be the best equation for that data. So we don't have to anymore go through that process of picking 2 points, finding the slope, writing the y-intercept and all that. We can, and to end up with something that's not consistent, we can just do this instead. All right, so remember in 611, we talked about that viewing tube data in the football field. So in that one, we just found the line of best fit. Now we're going to determine the least squares regression line, okay, which means now we're going to put this data into Desmos and we're going to have it do the work for us. All right, so I'm going to get rid of these guys. Okay, I'm going to go to plus. I want to add a table. And then I'm going to enter in that data about the amount of the field he could see. Okay, and then I'm going to enter in the width of his field view. And then I'm going to make sure I didn't screw anything up. Okay, so now from here on out, it is the same thing every time because these are still, I'm using X1 and Y1. So I'm going to have Y and then 1 with the tilde, and then B plus AX1. Again, when I do that, we'll talk more about what these mean in a minute. And in this one, my scale. So see how my scale, I have this still all the way up to 2,500. You can't see my data very well. I might change, like I might go from, I don't know, negative 10 to, let's see, what's my highest X? I don't know, maybe 150. And then here I might go, I don't know, negative 10 to, what's my highest? 21. So maybe I'll go 25. Okay, so now I can sort of see the data a little bit better, and you can see that line going through it. So that's a strong linear positive association. And then here's my A and my B values. So my B value is what, 1.659, so about 1.66. My A value is 0.134. All right, so then for my equation, it's that we're always substituting into this, right? So my equation would just be y equals my slope, that's my A value, is 0.134x, and then my y value is 0.166. So that's more accurate than what we had gotten when we did it by hand. Take care, algebra students.